Hello friends, today we will discuss about the role of hydrocracking technologies in the future of downstream industry and particularly in the context of fuel oil sulfur reduction. The necessity to reduce adverse environmental impact due to transportation fuel, particularly in the maritime space. Maritime industry has introduced a new stricter regulation to reduce the sulfur content in the maritime fuels, known as IMO 2020. This regulation mandates the maritime transportation fuel, that is called as bunker, to a level of 0.5 weight% sulfur maximum from a present level, that was operating level at that time was 3.5 weight% sulfur. And this mandate has created a lot of challenges for the refiners, particularly those who were actually processing very heavy and low value crude oil. So in this article we will discuss about the challenges that are being faced by the refiners, why they are facing those challenges, and a possible solution through the hydrocracking technology. Bunker production process before IMO 2020. In fact, this production process is even true today, but with some changes actually. So the maritime fuel oil known as bunker is relatively low viscosity fuel oil applied in diesel cycle engines to ship movements. Before 2020, the bunker was produced simply by blending vacuum residue, the de-asphalted oil, and to reduce the viscosity of the bunker or the marine fuel oil, we used to put diluent, some kind of diluents, which is the light cycle oil or gas oil. Since bunker was produced from high molecular weight residual streams, these are the high molecular weight residual streams, this used to contain a lot of contaminants like sulfur, nitrogen, metals. And that became a challenge for the refiners when the IMO 2020 came, that this bunker fuel oil, which was generally being produced around 3.5 weight% sulfur, is to reduce now to a level of 0.5 weight% sulfur maximum or below that. Since the new regulation post IMO 2020 mandates low sulfur level in the bunker, it becomes challenging for many refiners to produce low sulfur bunker through simple blend. In fact, many refiners will not be capable of producing low sulfur bunker because of their crude mix, because of their economics within the refinery, because of the particular crude mix they were doing and the configuration in their refinery. All these will increase the production cost of the bunker fuel oil, thereby putting pressure on the gross margin. On top of that, if you see, over a period of time, earlier the price gap between the 0.5% sulfur marine fuel oil and the 3.5% sulfur fuel oil was in the level of more than $300 per ton. But during the pandemic and during June 2020, those price gap has also reduced slowly to a level of around $38 per ton. So this reduction in the price gap has also challenged the refiner to actually being competitive, being profitable, even though producing a low sulfur fuel oil at an extra cost. Because to produce this 0.5% sulfur maximum, the refiner has to put some extra processing cost, and that processing cost will add up to their own profit margins. Apart from this reduction in the price gap, there was also a reduction in the bunker fuel oil demand for the high sulfur fuel oil. So that has added to the challenges for the refiner to produce a low sulfur fuel oil. You can see from this diagram in the figure where the green color bar, which shows the high sulfur bunker fuel oil, is slightly slowly reducing from 2019 to 2026, which is actually considerably reduced from, say, for example, around 3 million barrels per day reduction to around just a kind of less than 1 million barrel per day. On the other hand, the low sulfur, very low sulfur and marine gas, very low sulfur bunker fuel oil, the demand is increasing. So the price gap, the reduction in the price gap, combined with the reduction in the high sulfur fuel oil demand, has forced or is forcing the refiner to find ways to produce the bunker fuel oil mandated by IMO 2020 at whatever cost they can in the present scenario. In all these scenarios, in all this situation, one of the ways to get a low sulfur, although I will not say it is no extra processing cost is required, but relatively better solution is a hydrocracking process. There are two technologies where we can reduce the carbon footprint. Within that is one by carbon rejection process, rejection process, and another is the hydrogen addition process. So hydrogen addition process is better for a reduction in the contaminants in the fuel oil, and one of the best way to use the hydrogen addition process is the hydrocracking. And hydrocracking, as you can see in this particular, it is a two-stage hydrocracking process where the hydrogen is used at higher temperatures and pressures to react with the contaminants of the feed, that is the vacuum residue and the deasphalted oil, as well as other sources which the refinery will have, and then it reacts with those hydrogen reacts with those contaminants, and those contaminants are taken out from those feeds, and a cleaner fuel comes out, which then can be used for the blend purposes. In this particular slide, a schematic of the hydrocracking process is given, where the feed enters from here when it is preheated and then enters in a two-stage reactor where it is reacted with the hydrogen, clean hydrogen, at a high pressure of almost 35 to 260 bar and high temperatures of around 480 degrees Celsius. And once it is reacted, some part of the oil is cracked and some of the contaminants get reacted with the hydrogen, and once it is separated, some of the lighter hydrocarbon comes out, and the actual fuel that comes out is then can be used for blending. So heavier the feed, the higher the processing cost, higher will be the difficulty, higher will be the operating conditions, and so the processing cost increases. But this is one of the way to process and clean the fuel before it blends into the final fuel for cleaning up the environment or protecting the environment. Although this is just one of the technology, there are many other technologies, other process licenses for these kind of cracking process, and which can be selected based on the condition of the feed, other conditions of the hydrogen availability, or the process conditions into that particular refinery. With this, we come to the end of that. These are some of the references for this particular article, and we thank you for them to give us some information. If you want, you can go through these references, and thank you very much. And